Okay, well, my name is Dr. Tim Tuinstra, and I teach electrical engineering here at Cedarville. I'm here to talk to you today a little bit about using neural networks to do pattern recognition. You may wonder how I came to be involved in this particular area. It's been kind of a long story, but in my graduate research at the University of Dayton, which has been many years ago now, was looking at trying to automatically determine the size and morphology of lung cancer nodules from computed tomography images. So computed tomography, if you're not familiar, is an X-ray technique that we can look at slices of the human body and get cross-sectional information, images that prior to that we would have only been able to get by sawing someone in half, and looking at them we can now get without doing that, which is great. So we don't have to do that anymore. So in that study of finding the volume of lung cancer nodules, we needed a smart system or an expert system that was going to try to cut out essentially from the data the lung cancer nodules and show where their boundaries and their borders were. And so we had some radiologist data that the radiologists had gone and had done that by hand in the imagery, and then our technique was to be applied in lieu of a radiologist or as a second pair of eyes to create those, we call them segmentations, to segment out of the image where the lung nodule was at. So as part of that process, we used actually a different kind of a neural network than the one I'm going to show you today. But we used what we call a radial basis function neural network and applied that to our problem of choosing the correct segmentation. So that's another story for another time and another place. But as part of that, I became involved in this whole idea of neural networks as just one of the many tools in my tool belt to solve problems. So specifically what we're going to talk about tonight is probably actually related to what Dr. Gallmer spoke on a little bit last time. I was not able to be here, but I think he talked about, did you talk about clustering last time? So it's going to be a little bit related to that. In pattern recognition, what we're trying to do is we have some data set from some source. I mean, we all know the reason we're here is because the world is full of data. And we want to classify and clarify data, which data belongs with which group, and which data goes together, and try to create relationships between data. And that's a pattern recognition problem. We want to be able to look at data and say, is this an A, or is it a B, or is it a C? Automatically, we want to be able to do that. And that's a little bit of the clustering problem that Dr. Gallmer talked about. But we can do a similar kind of thing with artificial neural networks. So this idea of using a neural network is getting rather old. It's been around for a while. A little bit of the history, is that it was first approached in like the 1940s. And we'll talk about that in a minute. But first of all, let's just think about a neural network. What is the idea? The idea in science and engineering and math is to say, okay, humans and their brains are really, really good at certain kinds of problems. Did you guys ever think about that? Especially if you do computer programming at all, and you try to solve a problem through computer programming that a human can do. Sometimes it's very, very, very difficult. And the question is, why is that so difficult to do? Why is it? Give you an example. If I have a robot and I need to stay between, I got red things on the left and green things on the right, and I need to stay between them, why is it I can tell my 2-year-old to do that? But trying to get a computer to do that is hard. Why is that? So, God's the best engineer, right? God is the best engineer, even though much of the world doesn't recognize that. And so in the 1940s, some folks got the idea, what if we Instead of trying to write computer software from the ground up, why don't we try to write computer software that will try to mimic what we think is this, or what we understand to be the structure of the human brain, for example. So then they said, okay, well, what is the structure of the human brain? Well, this is a vast simplification here, understand that, but I'm going to give you the gist so that you can understand neural networks. Here's what a typical cell in your brain might look like. If you've had a biology class, you might recognize a cell like this one here. It has a cell body on the top picture on the left, and it has a bunch of little finger-like things that stick out. They're called dendrites. And the whole idea is that the dendrites receive some kind of information signals from other cells. Okay, and they're all networked together, as we'll see in a minute. But those inputs, those values, if you will, are taken into the dendrites, and some kind of processing goes on in the cell, some kind of adding them all up, and maybe a nonlinearity, which we'll talk about in a little bit. And then a new signal is produced, and that new signal goes out on the axon and then terminates in some more little fingers. And guess what those little fingers get attached to? More dendrites on other cells. Okay? More dendrites on other cells. And just to give a picture of what that might look like in 3D, I found this particular picture there. And so you have these cells, and they're just connected, and they're massively connected, right? All these dendrites going to all these axons, and so that the signals can ripple through this system. Okay? Another idea here is that the various dendrites have various priorities or weights. So the signals coming in some dendrites are more important than others. And as best as scientists understand it, which is even now I don't think all that well, those priorities can change over time as the brain and the system learns. And so in the 1940s, some folks got the idea, well, why don't we try to make this thing and see if it works, see how well it works. And thus was born the idea of artificial neural networks, or ANNs. Sometimes they affectionately call them ANNs, A-N-N. Okay? So that's the genesis of the idea, so to speak. So you go all the way back to 1940s, and these are some famous guys that kind of got the ball rolling. Warren McCulloch and Walter Pitts, and that was in 1943. So we have something called the McCulloch and Pitts neuron. So here was their idea. Well, let's create a neuron, an artificial neuron, which of course can be created in software. Okay, so here's the idea. Do you see anything you recognize here from the real neurons? These are equivalent to your dendrites, by the way, also called sometimes synapses. Okay, synapses. So these are the inputs. These are where the inputs are coming. And I have a couple different kinds of inputs here. By the way, so X1 is just, you want to think of these as just numbers. So X1, X2, X3, down to Xn, these are just inputs, they're numbers, they're values. Okay? Maybe I'm trying to tell what color something is in an image. Maybe I'm creating a neural network to recognize colors in an image. Maybe the X1 is how much red, and the X2 is how much green, and the X3 is how much blue. Just for example. Okay? So those are the inputs. They each get weighted. And in this case, for McCulloch and Pitts, their weights were weighted the same. Okay, we're going to see a little bit later that you want to change that, actually. But they weighted them all the same. And so these are called excitatory synapses. Okay? Then they added another feature that they also took from the idea of a real neuron cell. And these are called inhibitory inputs. And what these guys can do is they can outvote everybody else and turn this thing off. So the idea is this. You take a weighted sum of the inputs. Here's your summation, right? Take a weighted sum of the inputs. I think I have, let's see, those are, yep. Right. Okay, so if I have n inputs, and I add, and they're all either 1 or 0 for the McCulloch and Pitts neuron. These inputs are 1 or 0. If I add them all up, and they all happen to be 1s, I would have NW would be the sum. Do you agree with that? And then if any of the C's, if any of these are turned on, it automatically makes the thing go off. But the bottom line is, if NW minus C is greater than or equal to theta, you could think of theta like a threshold, then the output turns on. Otherwise, the output turns off. So it's a Boolean, it's a binary type of a neuron. That's the idea of it, at least. Okay? The McCulloch and Pitts neuron. So just as an example here, you can create things as like basic logic gates. Like from, I think many people, even math, I think you take digital logic design. No? Not anymore? Did you ever? You did? Okay. So and is basic. For some reason I thought math did. Maybe I'm thinking, anyway, it doesn't matter. Huh? CS does. Anyway, it doesn't matter. The point is, basic logic, right? If I have x1 and x2 can be true or false. So true and true is true. True and false is false. False and true is false. And false is false. Right? So a basic AND gate. So how does this gate work? This is a McCulloch and Pitts neuron with specific weights. What happens if I put x1 is 1 and x2 is 1? What will the sum be? What will the sum be? That's easy. It'll be 2. And the theta is 2. So if I'm greater than or equal to the theta, I'm on, so this will turn on. However, if one or the other of these are 0, then the sum will be 1, but that'll be less than theta, so this will turn off. And if they're both 0, it obviously will turn off as well. So just an example of a McCulloch and Pitts neuron used to be an AND gate. And so I think that excited them, right? That we can make an AND gate out of a neuron. All right, now I've got one for you to try here. Actually, I've got 2 for you to try. If you have a neighbor and you want to talk about this just for a minute, see if you can come up with a logical OR gate by appropriately setting the synapse weights. So maybe I'll go back on my slide. You understand you're going to make an OR gate? What's the truth table for an OR gate? Right. So both of them are off. False and false is false. False and true is true. True and false, true or false, I should say, is true. And true or true is true. So this is an OR gate. So I want you to try by appropriately sizing your weights. See if you can come up with an OR gate. Remember that the inputs will be either 0 or 1. The inputs will be 0 or 1. Theta you can actually leave to be the same. So all I have to change is W. What do you think? Right, you could do that too. If you change only W, what would you change W to make this into an OR gate? 2. You make this, if you change W to 2, you turn it into an OR gate.
What if you change theta to 1?
Yes. That would also work. Yep. So what's the bottom line? The bottom line is you can turn a McCulloch and Pitts neuron into an OR gate, an AND gate, just by appropriately sizing the weights. Okay? All right, I got one other one for you to try. Try this one, the bottom. Exclusive NOR means exclusive not OR, which otherwise, for those of you that have done digital logic, would be the same as not exclusive OR.
Is this with a single neuron?
With a with a single neuron. You might have detected a little question mark in Dr. Goldmer's voice there. I don't want you to work too long on this one, okay? Because you'd be here all night doing this one. Here's the thing, and I want to connect this to pattern. I want you to connect this to pattern recognition, because that's what we're talking about in this seminar, right? For the OR gate, we're trying to detect a pattern. Which pattern are we trying to detect? If these are your inputs, what pattern in words are you trying to detect or recognize?
Some greater than some value.
Okay, is the sum greater than some value? Or I could even boil it down a little simpler than that. What's common to all these three? That
There's at least one.
there's at least a single one in it, right? So you're recognizing the pattern, that there's at least a single one in it, right? And so those are recognized as ding, 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 I found the pattern over here. That's what this truth table is saying. Now, what's neat about this is I can represent these inputs in a plane, right? And so where's my zero? My zero is down here, right? This guy is not in the pattern, right? But where are the ones that are in the pattern? They're here, here, and there. Okay? In that space, notice that it's easy to do what? If I wanted to make a separation or a distinction between the two patterns, I need to make a boundary line, don't I? I need to make a boundary line of some kind. I can say somewhere right in here is the boundary line, and I can draw a line, a straight line, to do that. So that's what allowed me to be able to use a single neuron. If I can separate it with a line somewhere, then I can separate these with a single neuron. Now think about this one here. What's the problem? Obviously it's the opposite, right? My zeros are located where? At the, here, I'll change this one to blue, right? The blues are my ones, and my reds are my zeros. Now what's the problem? I can't draw a line that will separate those two classes. And so I'm not able to do that with a single neuron, and so that's the problem with this. I can't do that with a single neuron. Any questions or thoughts about that? It's the idea of recognizing a pattern. Yep.
Could you maybe use like inhibitors or something to, or just
The
that?
inhibitors, don't they have to be different than your inputs? Like the inputs to the inhibitors? Because if blue is like x plus n plus 1.
Right.
So they have to be like different. You can't use x, y, and x.
So what you really need to be able to do is do this. You can't do that with one neuron. Maybe you could do it with more neurons than that. And the answer is yes, you could. Yes, you could. Okay, any other questions on that? That's just to get us started. And I better get on my horse here. Whoops, that's not what I meant to do. meant to do this. Okay. Well, let's get a little more complicated than the McCulloch and Pitts neuron. Let's add a little bit of a capability to our neuron that is not there in the McCulloch and Pitts. And so here again, the idea is the same. You have your inputs, however many inputs you have, 1 through n. You're going to now weight them, but you're going to weight them by separate weights. You're going to allow the weights to be different. Okay? By the way, the subscript q is going to allow us to expand this to more neurons than just one. So this is the qth neuron, which has a qth, we call this a bias. Okay? Call this a bias that's added in. All right? And then these are the weights for the qth neuron. You see. So how does this work? We'll talk about this guy in a minute. I sum up my weights times my inputs. Right? I subtract off whatever the bias is. The bias can be 0 if I want it to be, or it can be something else. I subtract that off, kind of to center the whole thing maybe. Okay, to center everybody. And then I have this new piece here called the activation function. The activation function, okay? And we're going to talk about that in a minute. But the output then is the activation function applied to that sum. Okay? So let's talk about activation functions then a minute. What are they? Well, there's a bunch of different ones that we have. These are just a couple examples, and then one further example on the next slide. But examples of things we could do would be to hard limit. A hard limit would be the same as essentially thresholding. Okay? So let me go back one slide real quick, and then I'll come back. So if I make this be a hard limit, it's going to say if v sub q is less than 0, then y sub q will be 0. However, if v sub q is positive, then I'm going to turn it on. Okay? So again, the output in that case for the hard limiter will be either 0 or 1, either on or off or on, however you want to think of it. Well, sometimes that's good, sometimes that's not good. Here's another option that we could do. This is called a saturating limit. A saturating limit. And what's the fundamental difference between here and here? You're still either turning it off or on, but then you have this region, and this should be, I don't know if that's quite centered, but centered at 0 essentially. What's happening here? This is now letting me have a range of outputs coming out of my neuron. So not just 0 and 1, I can have a range, maybe from 0 to anywhere between 0 and 1. That adds a little bit of flexibility to what my neuron can output. But there's one other thing that I need to take into consideration that's going to come into play a little bit later, and that is this. From a calculus point of view, what would you say would be a unique feature from a calculus point of view of these activation functions? If you had to think calculus. You guys have all had calculus now. Would I have a hard time taking a derivative of these functions in some certain areas? I would. These functions are not differentiable everywhere, right? They're not everywhere differentiable. And it turns out that being able to be differentiated is an important part when it comes time to train our neural net. So we pick maybe something that looks like this. This is a hyperbolic tangent, which just says that the output then is to take the hyperbolic tangent of the input. That one is definitely differentiable, right? It has nice smooth curves. No problems there. The class of functions, by the way, that are used as activation functions are called sigmoidal. Anybody know what that word means? What does the word sigmoidal mean? I always am interested in words and their backgrounds. It means S-like. Okay? Did you notice that about all those functions? They all had the kind of the S look to them. All right. So this is an activation function that we commonly use. By the way, if you put in a constant inside the tanh function, you can control kind of how wide it is or how steep it is. All right. Yeah, it's differentiable. Yay. All right, so here's what we're going to do now. Here's what we're going to do now. In a neural network, what we try to do is to train the network to solve a particular problem. So there's a quote, learning process involved. And here's what we mean by training. Training a neural network means adjusting all the weights. Adjusting all the weights in some intelligent way so that for the training data, the output of the neuron or the network, because I'm going to put more than one neuron together, matches our desired output. So here's the kind of thing I'm going to do. I can say this. I can say things like, for image processing as an example, if the pixel is red, I output a 1. If the pixel is green, I output a 2. If the pixel is blue, I output a 3, just as an example. And then I present to the network red things. I say, here's something red, and for this, your output should be 1. Here's a green thing. For this, your output should be 2. And here's a blue thing. For this, your output should be 3. Just like we do to kids, right? No, it's not. That's not red. This is red. So you're doing that to your network. Okay? That's the idea. Training data. So you always have to have training data. And then you run the network against new data. That's the point. All right, so here's how that goes a little bit. This is just if I had only one neuron. And again, I got to get on my horse here. One neuron. What I'm going to do is I'm going to say, okay, here's my neuron that I had before. Now I'm going to introduce some feedback during the training process. I'm going to introduce feedback during the training process where I'm going to say, all right, compare my output of my network or my neuron to what I wished it was. It's probably going to be wrong at first, right? Just like kids are wrong and you have to teach them. It's going to be wrong at first, which means the difference is going to be non-zero. That difference is going to be fed back into what we call an adaptation algorithm. And the goal of that adaptation algorithm is to essentially fiddle with all these weights in some intelligent way to make it better. And then you start the whole process again. So it's an iterative process. Does that make sense? Present, train, look at the difference, adjust the weights, present again, adjust the weights, so on and so on and so on, until you're done, until your E sub k basically is 0 all the time. That's what you want. All right. Now, that's for just one network, one neuron. One neuron doesn't get us very far. We like more neurons. So here's the idea of what we can do, okay? And by the way, the math for this gets pretty involved, so I'm not even going to the math, but I want to explain to you at least what's here. All I've done is I've added neurons and I've added layers. Okay, so here's my n inputs. Each of my n inputs are going to be weighted and summed. The weights are down here. Instead of being scattered throughout, the weights are shown down here. Most texts show the weights as a vector. It's a vector of weights. Okay, add them up, run them through activation functions. So that gives me 1, 2, 3, 4 outputs. So here, well, n outputs. So I've got n neurons in this first layer. I can do multiple layers, right? I can do multiple layers. Here's the second layer. These are called hidden layers. This is called the output layer. Okay, so I got neurons, neurons, neurons. So all the outputs from these neurons then go into more neurons. Okay, so you can think of it like the axons from these go into the dendrites or the synapses of these, and so forth, until you get your, in this case, M outputs. You can have more than one output if you want. Okay, that's the idea. But the training remains the same. The training says, okay, here's some data. Here's what the outputs should be. Find the error, go back, adjust all the weights, do it again. That's what the training is. Okay? Any questions on any of that? So I think now it's time to try to show an example. Questions on the basic process? All right, let's show an example. I use MATLAB for almost everything I do. Some people use other tools. I know Dr. Goldmer, what is the tool that you use, Dr. Goldmer, for?
R.
You use R for neural networks, okay? So there's other tools. The principles all apply to the various tools. Okay, so I'm going to show you NPR tool. This particular tool, by the way, the MATLAB release that we have on the network here at Cedarville contains the neural network toolbox, which will let you do these kind of neural nets and many, many other kinds of neural nets that I'm not going to be talked about today. Okay? So this particular tool, NPR tool, is for pattern recognition. You see that in there. N pattern recognition tool. Okay? So let me get set up to show you that. All right. Here is the MATLAB interface that you have. I created a data set earlier today in order to demonstrate this ability here. So I'm going to load that. All right, so what I did, explain what I did, and then I'll show you some figures here. I created 3 different classes, just made up classes, okay? 1, 2, and 3. Each class is located in 3-dimensional space. Okay, so every time I take a measurement, I measure 3 things. And then I want to know if it's one of 3 classes. Does that make sense? Is it this, is it this, is it this, based on the 3 measurements that I make. That's the pattern recognition problem. Okay, so for example, the first class is class 1, and it has an x1, y1, and a z1, which are its 3 values. So I can say in MATLAB, for example, scatter. This would be a 3-dimensional scatter plot, and I would do x1, y1, z1. Okay, so there are my measurements for everybody that's a 1. Okay, then need to hold my plot. I don't know how familiar some of you are with MATLAB. I'll try to explain what I'm doing as I go along. I'm now going to scatter the next one. So x2, y2, z2. And I'm going to make this be a different color. Let's say red. Sure, fine. Red. And then finally, scatter 3, x3, go away, y3, z3. And we'll make that one green. Okay, so this is the data that I have. Okay, so if you're one of the red things, you're at all these locations. If you're one of the green things, you're out here. And if you're one of the blue things, you're down here. Nice thing in MATLAB, you can grab this 3D rotational tool and you can kind of look around and see where stuff is in 3 dimensions. That's kind of nice. But there's some problems with this data as far as trying to break out who's who, right? Because that's my pattern recognition problem. I want to know who's a green, who's a red, who's a blue. So what problem do I have? What are some basic problems? And by the way, these are real world problems. Real world problems are not nicely separated into, oh, the reds are over here, and oh, the greens are over there, and the blues are way down there. It's never like that. So I just gave away what the problem is.
There's overlap.
There's overlap. And you got one thing embedded in another thing, and a green coming in from the upper corner, and it's just kind of a mess. But you got to do the best you can, right? That's all you can do is the best you can. So, want to try to use a neural network to classify this. Okay? So here's how this is going to work. Here's how this is going to work. In order to do that, what I need to do is I need to put, I'm going to draw it on the board and then I'll show you in MATLAB. I need to put my data in an appropriate format. So I'm going to make a matrix. I'm going to make a matrix that has 3 rows by however much data I have. Okay, so every point in that scatter plot was one example. So I call them features. Things I measure, 1, 2, and 3, 1, 2, and 3, 1, 2, and 3, and so forth, up to n of them. That's how the data has to go in this particular setup. Then I need to be able to tell MATLAB what each class is. So in this particular setup, there's going to be 3 outputs for my neural network. Okay, the first output is going to turn on if it's the first class. The second output is going to turn on if it's the second class. The third output is going to turn on if it's the third class. So I need to create that. So let's say these all belong to case 1, and these all belong to case 2, and these belong to case 3. The way I would set up and tell MATLAB the training is I would say, okay, these are all 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, like that. So this says all these examples up here are all from the first class. Then this one is 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0. That idea there. Okay, so these are all in the second class. I've already set that matrix up. In this matrix I've called input. So if I double click that, you'll see what I mean. Maybe. What is? Oh no, those are my data. It's in output. This is my desired output. Sorry. So there you go. So you see, I put the first ones in 1 and so forth, and then at some point it jumps down. Okay? All right. Now, let's run the NPR tool. That's what you want to do next. So NPR tool comes up with this tool. By the way, there's several other neural net tools that are built into MATLAB. I'm not going to show you those right now. That's for another time. So you say, okay, that's the nice intro material. Hit next. By the way, it shows you kind of the architecture that it's going to use to start off with. So you got a hidden layer and you have an output layer. One hidden layer, one output layer, your inputs and your outputs. All right, you're then going to select your inputs and your targets. So my inputs are naturally input. And my targets are what I called output. It's this matrix that's set up like this one here. Okay? By the way, in here, if you want to play around with this at some point on MATLAB, you can load example data sets. There's some data sets dealing with cancer. There's and detection of cancer. There's data sets there's a data set about identifying various varieties of iris, which is kind of fun, like by petal length and color and blah, blah, blah. And so those are in there for you to play with as well, if you want to. All right, so then you go next. Now, this next thing shows how it's going to divide up the data. Usually when you do a neural network, I know this is kind of small font here, you partition the data into some training data and then some data that's going to be used for validation and testing. So MATLAB just defaults to using 70% of the data, and then it tells you how many samples that is out of my 1,500 that I have total, 1,050 samples. It's going to use that many to actually do the training, and then it's going to check to see how good did I do with the validation and testing portion. Okay, so if you like that, you just leave that alone. You say next. All right, and then you get to choose the number of hidden neurons. Okay, so that's the number of neurons in that hidden layer. Now, what's going to happen? There's a couple things that you have to be careful of when you are selecting the number of hidden neurons. And here's the rules of thumb. Well, here's the general idea. Too few of neurons is not going to be able to separate complex shapes in the space. Okay, so you don't want too few. And too many is going to result in lack of generalization. Now, what's generalization? You want to be able to train this data so that it will work on any data of this type. But if you use a whole lot of neurons, it's going to draw such a tight boundary that it will only work for the data that you're training it on, and it won't be general to other data of that type. So somewhere in there is some kind of a happy medium. Okay, and that involves a little bit of experimentation to deal with. So I'm going to actually just leave the number of hidden neurons at 10 for now. And I'm going to hit next. By the way, you notice that it shows you have 3 inputs, 3 outputs. 3 inputs because I have 3 values that I measured. 3 outputs because I have 3 classes. Okay, so I hit next. It says creating network. And now the network is created, and it's as simple as saying, okay, I would like to train my network. So you hit this nice train button here, and it does some stuff, and it says, voila, your network is trained. Now, how do you know how well it worked? How do you know how well it worked? Well, it pops up this interface for you to look at some stuff. And we don't have to go into all of it, but a couple of interesting things are the following. Number 1, how many times did it iterate? Here's what it does. The weights originally start off as just random numbers. Okay? The weights start off as random numbers. It then presents a pattern, says this is what the output should be, and then updates the weights. So it's going to do that over and over and over again until it reaches some kind of threshold of how good it has to be. So it took 63 iterations to converge. Okay, it tells you that there. It tells you how much time it took, which was basically nothing. Here's the convergence diagram. This is nice. If you pull that up, it shows you always want to see a downward trend. Okay, it's showing you for the training data, the validation data, and the test data. Okay, but the idea is that the trend is downward as it trained, and then it kind of leveled out. It's not going to get much lower than where it is now. Cross entropy is just a measure of how well it's doing. Okay. Here's another helpful measure of how well it's doing, and that is the confusion matrix. Here's the confusion matrix. And let's just look at the training confusion matrix. Basically, it's telling you how many things got misclassified. Okay? So you've got left to right, you've got target class, and you've got output class. So what happened here? We had, looks like it output a total of 356 plus 11 plus 8 and said those were class 1. 356 of the total there, which is basically 95%, it correctly categorized as 1, and it got 19 of them wrong. Okay? And so on. That's the idea of the confusion matrix. Just a measure of how well your network works. Okay? Questions about any of that? Okay? All right. Let's say that you decide now that that's a good network. I'm going to use that network. All you got to do is hit next. It asks you if you want to train again if you didn't get good results, and you say, no, that's probably good enough. You say next. It'll let you output a MATLAB function if you want to put that into a MATLAB function. I'm not going to do that particularly. It also lets you put out, those of you that use Simulink, which is a block-oriented design tool in MATLAB, it will let you output a Simulink block that will then become that network. That's kind of neat. But I'm not going to do any of that right now. I'm going to hit next. And what I'm going to look at here is it's going to give me the option to save the network to MATLAB as a network object named, and you can change the name of it if you want, named net. Okay, so I'm going to do that, and I'm going to say save results. As soon as I save results there, I can say finish. Are you sure you want to finish? Actually, I'll cancel. I'll just minimize that for now. Notice that my network now went to a MATLAB. We call this an object. So now my network is ready to be used. Okay? And so that's pretty easy to use then. All I have to do is, and I'm going to go ahead and run it on the data that I already have just to make life easier. I'm going to say out. That'll be my output classes. Out equals net. And then I have to operate on, well, where was my input? My input was in input. Okay. And it runs it just like that. And so now I can look at out, and we're going to make an important note about out here. What do you notice about out? That maybe you didn't suspect? It's not 0 or 1. It's not 0 or 1. Okay? That is because the output to those sigmoidal functions can be in a range from 0 to 1. So it's going to try its best, so to speak, to get as close to 1 or 0 as it can, but it's not going to be exact. So what do you think you would do at this point in time? You've run your network on some data, and what do you want to do now? You want to make a hard decision, right? You want to make a hard decision at this point in time, probably, okay? Because it either is in class 1 or it's not. It's either in class 2 or it's not. So all you got to do in order to solve that problem is just round it. That's an easy way to do it. You can round the output, put a semicolon after your command so it doesn't spit out everything. And now you have your output classes. Okay? And you could do things like plot that and scatter that and see how well that does. I did that earlier and it looked really, really nice. So that is basically the gist of the down and dirty how-to of using MATLAB to do neural nets for pattern recognition. So now I've said a lot of different things here today. Maybe it's a little bit like drinking from a fire hose. But any questions, application questions, questions about how you would set things up in MATLAB to solve a problem, any questions at all? Yeah, John?
So you said that it takes a little bit of experimentation to determine how many hidden nodes you should use.
Yeah, it does.
Is that essentially just manual labor of running through that window multiple times and comparing your outputs with the training data? Or
That's how I would probably do it. I'm not saying that's the absolute best way to do it, but that's how I would, I would choose a range of number of neurons in the hidden layer, and then I would kind of step through that at some step size and try things.
How do you know when you have overfit?
When you try it when you run it on new data, and on the new data, it doesn't classify well at all. So in other words, I would reserve out even some additional data. They automatically reserve some for testing and validation. I would only put maybe half of my original data to where I know the answer to train it, and then I would take this network now that I've created and run my second half and see how well it does against that. Yeah. That's a thought on that. Steve?
You get a little hint of that when you ran your model and you looked at your confusion matrix. The top left-hand corner was the confusion matrix with the training data, and then on the bottom left, it said with regards to the test data.
Yeah.
So when it split the data into two chunks, it trained on the first chunk. The second chunk, it did a comparison, and you can see how the statistics on the test data come out, and if they are still consistent with the training data, you probably will have good hope that it's going to be reliable.
Right. Yeah, that's a good point. Where did I was hoping I had there's my confusion matrix. So, not too bad, right? Here's the validation confusion matrix. 92%, 94, 93% overall. Yeah. Another way to look at it is something that electrical engineers a lot of times will look at least the origins of this curve come out of electrical engineering. It's called the receiver operating characteristic. And this originally came out of radar, okay? It came out of radar, which said, I got some signal. If the signal's big enough, I'm going to say that there's an aircraft out there or a target. If it's not big enough, I'm not going to say there's no target. So I got to set a threshold, right? Your receiver operating characteristic says, as I change thresholds, okay, what is my false positive rate to true positive rate? Now, what does that mean? True positives are ones that I called positive, let's say classes. Ones that I called ones that were actually ones. Values that were classified as a 1 that were actually ones. It's my true positive rate. My false positive rate would be ones, you gotta not use that word ones, would be objects that I called a 1 which were actually something else. Okay? So I don't want the false positive rate to be 1. Do I? And I don't want the true positive rate to be 0. I want to be up in here somewhere. The best I could do would be a true positive rate of 1 and a false positive rate of 0. That would be the best I could do, right? So what I want to look for is how good is the knee in this curve. I would really like this curve to come straight up, take a right-hand turn, and go this way. The farther down these curves move from the corner, the worse I'm doing. So that's another visualization of it. You can see that the training does really well, but that's because we trained on that data. You can see that the validation and the test receiver operating characteristic falls off from that a little bit for class 2 especially. All right? And so we might want to investigate, well, why is that, and can that be improved at all? Yeah, Josiah?
So what does it mean that the training data wasn't classified correctly? Is that like the training data is put back into the neural network after we already have determined the weights?
It's right, essentially. Yep. Because there might be some training data that as close as we can get is wrong. You see what I'm saying? Because I'm trying to, remember with the training, I'm trying to adjust all those weights so that every example I put in gets classified correctly. But there's some examples that no matter where I train those weights, I'm never going to get the right answer, just because of the nature of how it is. That brings another, just really quickly, is the training is meant to be intelligent, okay? And I didn't have time to talk about how the training works, but it's got to be something better than random. Because one way to train the system would be just to keep presenting data and randomly adjust the weights until you get the right answer. But how long do you think that's going to take? You have to do, you've got potentially hundreds of weights, which means how many different combinations of weights do you have? Many more than there are probably atoms in the universe in a lot of cases, which means you're never going to do an exhaustive search of the weight space. So you have to search intelligently in some way. There's algorithms that are used to do that called, what's that?
Backpropagation.
Well, backpropagation is the idea of working back, but the way that we adjust the weights we would do by like linear mean square and gradient descent and things like that, where we essentially look at how the error is changing as we change the weights. We essentially get a derivative, which was why that activation function needed to be differentiable. We essentially look to see how the error is fluctuating as I change the weights and use that to tell me which way I should adjust all the weights to go downhill. It's a minimization problem, absolutely. Absolutely. Yep. So, okay. Any other questions? Yep.
I can't help but seeing like the neural network as a graph after taking graph theory.
Sure.
How much, like, does that play a big role in it, or is it just kind of like graph theory in general? Is that helpful? Or is it more of what we've been talking about?
Well, I think you could cast some of the neural network stuff as graphs. I can't think right off the top of my head of the exact connection, but certainly you're right to see graphs and nodes there. Yeah. Yep. Any other questions? You guys have been patient and good. Yeah, Dr. Gomer?
You're talking about minimization problem. Is it possible to get caught into a local minima and not catch the global minima?
I've heard of that.
I think it probably is.
Depending on the algorithm.
So I was wondering if neural networks do, maybe different start points and then compare multiple nets to see who gets the best results.
Mm-hmm. That's an excellent point. You can get in one dimension, right, guys? You can the function of the weights. You're trying to minimize a function, which is the error. right? Your error, if it's E, is some function of all these weights and all these layers. So there's many, many, many weights, right? Dot, 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 dot. And that function can have many ups and downs in it, and it's highly nonlinear, right? So that's an excellent question. Where you start matters of where you end up, potentially. And there's also the idea of step size, okay? In terms of when you turn the weights, how much do you turn them? If you say, okay, this way is downhill, I need to turn this one so much, and this one so much, and this one so much. If you turn them just a little bit, you're going to have the opportunity to get stuck in a local minimum. If you turn them more, you might get up and over a mountain in this function, right? So that can often be set up in the training part of the algorithm, that step size. In fact, I have here, real briefly, I have one of the basic weight update equations, and it says this. I'll show you what I mean. This says that the new weights, okay, is equal to the old weights. Okay, so think of these as vectors. W has a whole bunch of numbers in it. This is the last one with a whole bunch of numbers in it, plus some mu E of k. This is your error. So the bigger your error, the bigger this term is going to be. And then times x of k, where you are in the function. So right here, this is pretty important, because you can set this size. This tells you how big of a step you take when you're exploring your weights. If you make it big, you might get up and over a mountain, but you also might jump right across a valley. What might you do in your training? You think it's better to start off with big step sizes or little step sizes, or what?
Maybe start off with big and then go small.
Absolutely. Start big, get smaller, smaller, smaller as you get lower, lower, lower in your optimization. Yeah. That's an idea. So essentially make this guy, they've got this guy as a constant, make this guy be a function of what iteration you're on. Yeah. All right, anything else? I've kept you guys for over an hour talking about this stuff. A couple good books, just by way of if you want resources on this. I like this one pretty well, Principles of Neurocomputing for Science and Engineering by Ham and Kostanik. I got most of the stuff in this presentation. This was helpful for that. This is an old kind of classic book. Bart Costco is kind of an interesting guy. He's got like 5 degrees in like law and science and engineering and I don't know what. He's just kind of a jack of all trades kind of a guy. But neural networks and fuzzy systems. Fuzzy systems are separate from neural networks, but his coverage of neural networks is good in there and interesting. He's readable. And then in this book, this is Artificial Intelligence, a modern approach. But they have a section in there on neural nets. And then this book here, An Introduction to Biological and Artificial Neural Networks for Pattern Recognition, is written by a friend of mine, Stephen K. Rogers. Not the Stephen Rogers from Captain America, although he signs his emails as Captain America. Good introduction to neural nets. I learned a lot of the stuff I learned about neural nets from Stephen Rogers, who's a local guy here, at least last I knew. So, former Air Force guy. Okay, well, thank you for your attention. Appreciate each of you coming.